Hello everyone, welcome to Organic Chemistry Hub. Today we'll be discussing on intramolecular aldol condensation or reaction. Intramolecular aldol reaction or condensation. So if a compound containing two carbonyl compounds, if that undergoes an intramolecular aldol reaction, if five-membered or six-membered ring is formed, that process what we are calling intramolecular aldol reaction. So if the compound containing alpha, two carbonyl compound, that carbonyl compound must containing alpha hydrogen. Those compounds only will give the intramolecular aldol reaction. So for example, I'll be taking this CH3 C double bond O, CH2 CH2, C double bond O, bond H. In the presence of diluted sodium hydroxide at high temperature, I'll be getting directly the ring cyclized, or cyclized product. So here we must understand there are three alpha hydrogens in the molecule. With respect to this ketone, this is alpha. With respect to this ketone, again this is alpha hydrogen. With respect to this aldehyde, this is alpha hydrogen. But as we know, 5-membered and 6-membered rings are highly stable as comparatively 3, 4 and 7. 3-membered, 4-membered, 7-membered rings are generally unstable. So if I go through the mechanism, now as we know, aldol reaction basically involves three steps. The first step is generation of carbon ion by abstracting the alpha hydrogen using base. The second step is involving nucleophilic addition to the carbonyl. The third step is involving dehydration reaction. In the first step, proton abstraction should take place. Now, if you look at this one, there are three different alpha hydrogens are present in the molecule. Now, if sodium hydroxide abstract this proton, for example, so here once we create a negative charge on this carbon, this will undergo nucleophilic addition to the other carbonyl group. Okay, if you look at this, I'm going to shift this one to like this. This is now there is a three-membered ring formation. If I create negative charge here by abstracting the proton, this will undergo nucleophilic addition to this carbonyl three-membered. The finally what we have here is this is the alpha hydrogen. If you abstract this proton, what we get here is negative charge. The negative charge will undergo nucleophilic addition to this carbonyl. So we have to count the what is the membered ring formation. 1, 2, 3, 4, 5. So that is why we are getting this product. So 5 and 6 membered rings always we should get in this intramolecular aldol reaction. Okay. So what is the mechanism is involved? So I'll be taking this example and OH minus. Here we have bond H. The proton abstracted by base and you get CH2 C double bond O, CH2 CH2 C double bond O, bond H. What we get here is negative charge. Okay. Next, this act as a nucleophile. Anyway, we are removing water. Now this act as a nucleophile. This will undergo nucleophilic addition to this carbonyl group. So finally, what we get here is the cyclic member ring where you have O minus and here C double bond O. I know you are a little bit struggle. I know you will struggle a bit on that how to make the bond for ring formation. So what I will do, I'll just give numbering here. Okay, if still not understanding. So I'll give numbering. Well, this is 1, this is 2, this is 3, this is 4, this is 5. So let me put it in this way. This is 1 now, this is 2, this is 3 and 4 and 5. Anyway, 1 and 5 bond formation is taking place and second position we have C double bond O and fifth position the O minus is formed. As we know, if we add water So what will happen? The O minus abstract the proton from water to become OH. Now this is beta hydroxy, right? This is beta hydroxy. So this is now beta hydroxy ketone. At very high temperature, we have to eliminate alpha hydrogen and beta OH. Then only we'll get most resonance stabilized double bond. So finally we'll end up with here double bond and C double bond. So this structure, both are same. You do not worry about that. So let me take the one more example. So if I take now the benzene, C double bond O, CH3 and CH2, C double bond O, bond H. The same situation here, diluted sodium hydroxide, again heat. So here there are different alpha hydrogen. If you look into it, this is now alpha hydrogen. So this is also alpha hydrogen. But which proton should be abstracted by base to give the proper ring formation? So here the sodium hydroxide, if this proton will abstract by base, what happen? This will undergo nucleophilic addition to this carbonyl. That means what kind of membered ring is forming? 1, 2, 3, 4. So 4 membered ring formation is taking place. The proton abstraction is not favorable. So now if I abstract the proton the other side, so here this will undergo nucleophilic addition to this carbonyl. So 1, 2, 3, 4, 5, 6 membered ring you are getting, that is more stable. So same thing, if you are not able to write the whole mechanism, the one shortcut method I'll be taking. So after choosing the best alpha hydrogen, there two hydrogens we have to take, and in another carbonyl we have to take the oxygen group. So we have to eliminate water directly. If you eliminate water directly, you will end up with here double bond. Okay, double bond, and finally this is what you get. Okay, this is one more example. You can also take the one more example where you can take something like this, C double bond CH3 and diluted sodium hydroxide at high temperature. So here what is happening? Here again you see different again alpha hydrogen, either this one or this one. The molecule is symmetrical, so any side you can able to abstract the proton. This is now alpha, this is now alpha. So both, this is minimum molecule is symmetry. Either you can create here, create, you'll get the same product. So now we have to understand what type of product that is possible. 1, 2, 3, 4, 5, 6. If I abstract this proton here, I'll get 6 membered ring by adding directly to this 6 membered ring we get. If I abstract this proton, 1, 2, 3, 4 we are getting. So this is not possible, this is possible. You know, right? What is the shortcut method? This, no, we have chosen this alpha hydrogen. Here two hydrogens we have to take. Here we have to take one oxygen. So if you eliminate water, you get the double bond. So let me write it in simple way for your understanding. So I'll simplify this. Okay, the structure we can easily eliminate. Okay, water. So there are 3 carbon atoms. I'm going to write it here. There is a C double bond O CH3. As we discussed in the last slide, also same thing. So we have to eliminate, after choosing the best alpha hydrogen, we have to choose 2 hydrogens over there. The other carbonyl one oxygen we have to eliminate here water. After eliminating water, directly what I am getting here is double bond C double bond O, and finally 1, 2, and here this is what we are getting, and also we have methyl group. Okay, so when you do this shortcut method, you will end up with alpha beta unsaturated carbonyl. But if you want to get beta hydroxy, I have already explained in the Aldol reaction a trick or shortcut method. Please go through that video. Thank you for watching. Please subscribe and share to your friends also. Thank you.